Hello and welcome to our second video on 2-10. The 2-10 class notes are kind of taking us to our next way of looking at energy. We mentioned earlier that phase changes can take in energy or release energy, but so can chemical reactions. And that is one of the driving forces. Energy changes in a chemical reaction is one of the driving forces behind chemical reactions. The other driving force is entropy. So if someone said, why do things react chemically? The answer is because the universe is tending towards lower energy. In other words, chemical reactions happening that release energy tend to happen in the world. And that's because as the energy is going down, the stability of the substances in the universe is going up. The other driving factor is entropy, where everything is tending towards greater disorder in the universe. Those are the two driving forces. But let's take a closer look at energy changes in chemical reactions. First, let's take a look at what happens when a chemical reaction occurs. The first thing that happens is when we put the reactants together. Those are the things that are going to undergo chemical changes. When we put them together, the substances must collide with sufficient energy to break the bonds that are already there. So let's say I have two molecules. I have a molecule right here, and I have another molecule right here. And these things are going to react chemically. In order for them to react chemically, these two molecules must slam into each other with enough energy that the bonds that are holding those things together break. So they start off together, they slam into each other, and when they slam into each other, the initial bonds, whether they're covalent, ionic, metallic, those initial bonds have to break so that everything in that reaction can find new partners. When they collide with sufficient energy, they have to collide in the proper orientation so that the bonds break. So what that means is I might have two molecules like this right here. If they collide head on, slam, they might not break apart very well. But if they collide where one is facing this direction, the other's facing that direction, if they collide, they then can break the bonds if they're colliding the right way. So like a perpendicular slam might break them apart easier than a longitudinal collision. And then the third thing is when they are once broken apart, they have to find two new partners. So here I have this blue molecule, I have this white molecule. They collide with enough energy, they collide with the proper orientation to break the things apart. Boom, they break apart. Now the blue ones, if they join up with the white one, we would have new molecules. We would then have two new molecules. The white ones started with the white ones. The blue ones started with the blue ones. They slam, enough energy, right orientation, they break apart, new things form. Notice it said that they have to collide with enough energy. So reactions must take in energy. So here we are. We're starting with these things. If they don't have enough energy when they hit, they can't break apart. So if they're going really slow and they hit, they would just bounce off each other. If they're going fast enough when they slam into each other, then they can break. The average kinetic energy of the molecules in a substance is called temperature. To increase the temperature, we have to add heat energy. Heat energy will get the average kinetic energy up so that more of them can slam into each other and then they break apart. But reactions take energy initially. Reactions take in energy initially. That's an endothermic process. All reactions must take in some energy initially. That's endothermic, to break the initial bonds. The energy that they take in to break the existing bonds is called activation energy. Activation energy means that you're going to activate the reaction by breaking apart the atoms. But then they will release energy as new bonds form. So once they break apart and they find new partners, new bonds form. if these atoms end up bonding with another atom that makes them more stable, remember, when stability goes up, then the energy goes down. So when they break apart from their initial partner and they find a new partner, if that new partner makes them stable by giving them the right number of electrons, the octet rule, if they needed 8, the small atoms only need 2, that's the duet rule. But if they get electrons in the configurations that they want the electrons, and that makes them chemically stable, they release energy. That's an exothermic process. They release energy. If they're made very, very stable, they release a lot of energy. If they release more energy than it took to break them apart, if the energy out, the energy that was released, is more than the energy it took to break them apart, you have an exothermic reaction. What would that look like if we were going to graph it? Here's the graph of an exothermic reaction right here. In an exothermic reaction, the overall energy change is the energy moves from the system, that's the atoms in the reaction, to the surroundings. That's what is around the reaction. If energy is moving overall outward, it's exothermic. Exo means energy exits. Let's take a look. Here on this axis is energy. On this axis is reaction progress, or time. Here's where the reactants start. So the reactants in this reaction would be, there, the reactions in this, we start with these guys right here. Here's our reactants, the blue molecule and the white molecule. The blue and the white, the blue and the white. Those are our reactants. Remember, in this reaction, we have to break them apart. That takes energy. So to break them apart, we have to add energy. It's exothermic. So we break them apart. We add energy. It's exothermic. Now, if they form new bonds with a different partner, and it's very, very stable, they begin to release energy. They'll begin to release energy. So at this point, we added this much energy to break them apart. New bonds are forming. Those new bonds are stable, so it releases a tremendous amount of energy. Energy is going down as it releases it. Overall, it's exothermic. Why? Because overall, the energy went from right here on this line down to this line. From here down to here is the amount of energy that was released overall. That was the overall energy change. It was lowered, so it would be a minus delta H, a minus triangle H. That means the overall energy change was negative. It went from this line down to that line. Remember, in the universe, those reactions tend to want to happen because the products, the blue with the white is more stable than when the blue was with the blue. So the products are now more stable than the reactants. Reactions can happen as well that take in energy. We'll talk about that in a minute. How will I know an exothermic reaction happens? Well, let's say I have a reaction container. And in this reaction container, I put in a thermometer. Can you see the thermometer? Let's say I fill this thing with water. And then I put in the things that are going to react. The white balls start off with the white ball. The blue balls start off with the blue ball. And we add energy to break them apart. We're adding energy to break them apart. And when we're done, the white hooks up with the blue hooks up with the white. How will I know if it's exothermic? By monitoring the temperature. The water's temperature should actually go up if it's releasing energy. The system are the atoms. The surroundings was the water. The thermometer is measuring the temperature of the water. If the temperature went up in the water, it's because the reaction released energy. Exothermic, it would feel warm to the touch because the system is releasing energy to the outside. The opposite can happen as well. let's say that these reactants are very stable. The blue wants to be on a molecule with the blue. The white wants to be on a molecule with the white. They're very stable. If they're stable, that means they want to be together. They're being held by strong chemical bonds. To break those strong chemical bonds, it's going to take a tremendous amount of energy. So we're looking at this graph right here. Here's the reactants. They are very stable. To break them apart, I have to add tremendous amount of energy. My activation energy is right here on this line. From here to here, that is how much energy it took to activate the atoms, to break the atoms apart, to smash them. It took a lot of energy. When the reaction was over, the blue joined up with the whites. But they may not have wanted to form these molecules. These molecules might not have made them as stable as they were when they started. So if they are not as stable when we started, if the stability is lower, then the amount of energy it releases is going to be significantly less. So here's the energy it took to break them apart. If they're not very stable, then they're not going to release as much energy. If the energy is low, it's not releasing much, then the stability was not improved. The stability was not improved. Why would that happen? Why would stable molecules break apart to form less stable molecules? Answer: it might have increased the entropy. Remember that there are two driving forces, and the second factor was entropy. If we increase the entropy, maybe we started out with reactants that were solids, and when we finished, we produced products that were gases. They're free to move out as gases. The entropy increased. When entropy increases, delta S increases. That can drive a reaction to happen. That can drive a reaction to happen. But in this case, it took more energy in than was released. The energy started on this line right here. When we were finished, the energy was on this line right here. The overall energy went up. The only way that could happen is if it took in energy overall. Taking in energy is called endothermic. Endo means it took in energy. The overall energy went plus. Energy change is triangle. The overall energy or enthalpy change was raised upward. The products had higher energy than the reactants because they are less stable than the reactants. As it says right here, the products are less stable than the reactants, but they must have had higher entropy in order for that reaction to occur. The reactants could have been a very large molecule which broke apart into multiple small molecules in the product. A big thing falling apart into small things would be an entropy increase. The small things might not be as stable as the big thing. So when the energy went way, way up, when it took a lot of energy to break it, and less energy was released in the process of forming the new bonds, that is an endothermic reaction. So that is energy changes with respect to chemical reactions. The only reason we're talking about that now is because we learned exo and endo with regards to changes in states of matter. So why are we talking about them now with chemical reactions? Because we know energy changes accompany chemical reactions, as we learned in Unit 1. We're just talking about how that occurs. How can energy be taken in or given off in a chemical reaction? If you have any questions or confusion on these notes, don't hesitate to email me or set up some office hours to come in and see me. Thank you for watching. Have a great day.